Hello everyone, my name is Navid. I'm going to talk about our recent result in kernel density estimation. This is a joint work with Moses Charikar, Michael Kapralov, and Paris Siminelakis. Since the talk is about kernel density estimation, let's start with kernel functions. A kernel function receives 2 points P and Q as input, and then its output is a quantity between 0 and 1 that measures similarity between these 2 points in RD. The main property for the purpose of this talk is that this is a decreasing function of distance between P and Q. One can think of Gaussian kernel, exponential kernel, and etc. For the most of this talk, we are going to focus on Gaussian kernel. Suppose that we have a dataset P in our space RD, such that size of P is n. Then kernel density at some point Q is defined as the average of kernel values between data points and our point Q. We usually denote this value by mu. The points in the dataset can be viewed as some samples from some density function, and this kernel function is going to smooth out these samples so that they generalize to the whole space. In kernel density estimation problem, we have a kernel function k, a set of points p of size n. We are going to first prepare a data structure in the pre-processing phase. Then in the query phase, we are going to be given a query point q in space RD. Our task is to output a 1 plus minus epsilon approximation to the kernel density at q. For simplicity, let's assume that epsilon is constant, and we want to succeed with constant probability. Also, without loss of generality, we are assuming that d is polylog n. This problem has many applications in machine learning, statistics, and data analysis. Let's start with a trivial solution for this problem. Suppose that in the pre-processing phase, we are just storing the data points. And in the query procedure, we are going to go over all these data points and calculate the kernel value between these points and our query, and then output the average. This is going to have space order n and query time of order n, which is linear in the size of the dataset. But this is not satisfactory. Remember that we want to approximate summation of some quantities, so we can do random sampling. Suppose that we are sampling a data point uniformly random from our dataset in the pre-processing phase. And in the query procedure, we just output the kernel value between this point and our query. The question is that if it is a good estimator or not. We need to check two properties. First, we need to check if it is unbiased or not. And the second question is that what is the variance of this estimator? Let's do the analysis for random sampling more carefully, because this is going to provide us a benchmark to compare our algorithms. The first moment of this estimator is obviously equal to the kernel density, so this estimator is unbiased. For the second moment analysis, we can see that expectation of z squared is upper bounded by mu. This is just achieved by noting that kernel values are upper bounded by 1. Now, using standard techniques, we can see that we need order 1 over mu samples to get a 1 plus minus epsilon approximation to our kernel density. The space consumption of this data structure is order 1 over mu, and the query time is order 1 over mu as well. This already suggests that mu is a nice parameter to state the space and query times in terms of. One can think of mu as some quantity between 1 over n and 1. Now let me tell you about the prior work in this area, and then a little bit about our result. Charikar Siminelakis, in their Fox 17 paper, were able to beat random sampling for the first time and achieve space of order n over root mu and query time of 1 over root mu. In the follow-up work of Bachkurs, Charikar, Indyk, and Siminelakis in Fox 18, they were able to achieve linear space and constant query time for smooth kernels, such as polynomially decreasing kernels. And more recently, Bachkurs, Indyk, and Wagner were able to improve the space of FOX17 paper to get space of order 1/mu. In this result, in the first part, I'm going to present a data-independent approach that is easy and simple to analyze. It is so simple that I will be able to give you almost all the details about it. And this already improves upon or matches all prior work in this area up to polylogarithmic factors. More specifically, for the Gaussian kernel, we are going to have a data structure that has space of order 1/mu, and its query time is 1/mu raised to power 0.25. The approach is not special for Gaussian kernel, and it can be applied on other kernels as well. In the second part, I'm going to talk about a more technically involved data-dependent approach that we had, which improves upon the first part of this result. More specifically, for the Gaussian kernel, we are going to improve the query time from 1/mu raised to power 0.25 to 1/mu raised to power 0.173. This approach is also general and can be applied on a broad class of kernels, but not all of them. Let's get back to random sampling, and remember that in random sampling, we were choosing points uniformly random from our dataset. But the question is that what is the right distribution to sample from? This leads to important sampling. Ideally, we want to sample points with probabilities proportional to their contribution. More specifically for this problem, ideally we want to have the probabilities that are equal to 1/n-mu times their contribution. 1/n-mu is the right normalization factor since the summation of these kernel values is equal to n-mu. Now let's design an estimator. Suppose that we choose points with probabilities 1/n-mu times their contribution. Then we need to set our estimator to be 1/n times 1/probability of sampling this point times its contribution. If you look at this estimator closely, you will notice that it's always returns the right kernel density. But the problem is that beforehand, we don't know what the exact value for mu is. So we are going to use a constant factor approximation to mu. This is going to give us probabilities that are just a constant factor away from the right probabilities. And then we will need constant number of samples to get a 1 plus minus epsilon approximation to our kernel density. In importance sampling, we are sampling points with higher contribution with higher probability. In our problem, which points have higher contributions? Of course, the points that are closer to the query, since kernel is a decreasing function of the distance. Now we need a primitive that samples points that are closer to our query with higher probability. This leads us to locality sensitive hashing. These are space partitioning schemes that closer points hash into same bucket with higher probability compared to far points. This has applications in approximate near-neighbor search problem, range reporting, and etc., and has received a lot of attention in the area in the recent years. The hash family that we are going to use in this work is Andoni-Indyk LSH. Andoni-Indyk LSH is a space partitioning scheme that uses ball carving to partition the space. The informal guarantee is that for any 2 points P and Q at distance r, their probability of collision is Gaussian in distance r. More specifically, it's approximately equal to e to the minus r squared by 2 eta for some eta. Charikar Siminelakis in their FOX17 paper, they used Andoni-Indyk LSH for sampling. In the pre-processing phase, they first hash points into buckets using Andoni-Indyk LSH. Then when a query comes, they look at query's bucket and uniformly sample a point from this bucket. Their algorithm and data structure is nice since it improves upon random sampling, but the difficulty is the variance analysis for this estimator, since there are some dependencies caused by Andoni-Indyk LSH and the geometric structure of the problem. And actually the variance is not good, since by setting of the parameters, they get that the probability of sampling some point is proportional to square root of kernel value. This results in query time of order 1 over root mu for Gaussian kernel, for instance. Now let's see how we approach this problem. Let's first start with some simplifying assumptions. First, assume that we have a constant factor approximation to mu, and for simplicity, we call it mu here. The second assumption is that we scale points in such a way that kernel value between 2 points P and Q is mu raised to power distance squared by 2. The second assumption is that we assume that we have no points beyond root 2 from the query. The intuition behind this assumption is that points at root 2 are contributing mu to kernel density, so points beyond root 2 are going to contribute smaller amounts, so we can kind of ignore them for now. These three assumptions are without loss of generality. Let's get back to ideal importance sampling and recall that we wanted to sample points with probability 1 over n mu times their contribution. Suppose that we have a point at distance x. So we want to sample this point with probability 1 over n times 1 over mu raised to power 1 minus x squared by 2. So let's do the following. For any distance x, first sample the whole dataset with this rate, then prepare a data structure in the pre-processing phase, such that when a query comes, if a point at distance x was sampled in the subsampling phase, we would be able to recover it efficiently with higher probability. We are actually going to use Andoni-Indyk LSH for recovery. So after subsampling the dataset, we just hash points using Andoni-Indyk LSH, and in the query procedure, we scan query's bucket for points at distance x, and we recover. The efficiency of this algorithm comes from the number of points that we are going to scan, more specifically, the size of query's bucket. We want at most constant number of points in query's bucket. In order to achieve this, we need to set parameters in such a way that we get constant number of points from each distance in our query's bucket. First, let's look at collision probabilities using Andoni-Indyk LSH. For simplicity of the calculations, we are stating the collision probabilities in terms of mu. Assume that it's mu raised to power alpha times x squared for some alpha that we are going to set, and we can achieve this family by just concatenating a bunch of Andoni-Indyk LSH hash functions. The second property that we need to check is density constraints. This is a nice observation that we made about the dataset. We ask the following question. We ask how many points at distance y can we initially have in our dataset. Remember that points at distance y are contributing mu raised to power y squared by 2. So we can have at most n times mu raised to power 1 minus y squared by 2 of these points. Since if we had more points, the density at q would be higher than mu, which is not possible in this case. The proof is just one-liner, as you can see in this slide. Now let's do the analysis of query's bucket size. For now, let's look at points from distance root 2 in query's bucket. Initially, we can have at most n points from root 2 in our dataset. After subsampling, we are going to have at most 1 over mu raised to power 1 minus x squared by 2 in expectation. Now we use Andoni-Indyk LSH to hash these points. What is the collision probability for points at distance root 2? This is approximately equal to mu raised to power 2 alpha. So we are going to have at most 1 over mu raised to power 1 minus x squared by 2 minus 2 alpha points. Our goal was to set the parameters in such a way that the size of our queries bucket is constant. So we need to set the exponent here to be 0. More specifically, we need to set alpha to be 1/2 times 1 minus x squared by 2. Here, I just gave you the analysis for the points at distance root 2. If you want to see the analysis for any distance y, you can take a look at these slides that I'm just flashing. This is just some arithmetics, and here we actually see that by simple arithmetics, the worst case is actually for y equal to root 2, and we need to set alpha to be 1/2 times 1 minus x squared by 2 to get constant size query buckets. Now we can do the query time analysis. Remember that we were interested in recovering points from distance x in queries bucket, but they hash into queries bucket with probability mu raised to power x squared by 2 times 1 minus x squared by 2. So we need to repeat this procedure 1 over this probability times to recover these points with high probability. So for any distance x, we are going to spend 1 over mu raised to power x squared by 2 times 1 minus x squared by 2 times. And as you can see in this figure, this exponent is upper bounded by 0.25. We are going to repeat this whole procedure for order log n distance levels from 0 to root 2. So all in all, our query time is upper bounded by 1 over mu raised to power 0.25 up to polylogarithmic factors. Now let's do the space analysis for this data structure. Remember that for distance x, we were sampling points with some rate, and then we were hashing these points a bunch of times. So in order to analyze the space of this algorithm, we need to multiply the number of initial points n by the sampling probability, and then number of times, and then multiply it by the number of times that we hash these points. And as you can see, this is upper bounded by 1 over mu for any distance x. So the space of this algorithm is upper bounded by 1 over mu. So in summary, for the Gaussian kernel, our space is bounded by 1 over mu, and query time is bounded by 1 over mu raised to power 0.25. The approach and the ideas used in the analysis is general, and it can be applied for other kernels as well. So far, we have used data-independent LSH from 2006, but the area has developed since, and now people are using data-dependent LSH in that area. Can we use these data-dependent LSH techniques to improve upon the result of the first part? Let's start with basics of data-dependent LSH. First, assume that the dataset always lie on a sphere instead of the whole space. Instead of doing ball carving in RD, we use spherical caps to partition the sphere. And always we want to reduce to a case when the data points are uniformly spread on the sphere. So the general approach in data-dependent LSH is a recursive hashing scheme, meaning that first we are going to hash points into large buckets, and then we are going to hash these large buckets into smaller and smaller buckets in a tree-based fashion. General procedure can be summarized as follows. We are going to find and remove dense clusters on spheres until no such cluster remains. Now we are going to use spherical caps to partition this space, partition the sphere into some hash buckets, and then we are going to recurse on each dense cluster and each hash bucket. The takeaway point from this slide is that we only use spherical hashes when the points are uniformly spread on the sphere. Also, note that when we were doing this subsampling, we were looking at distances y, And we know that the upper bound, the number of points at distance y, is upper bounded by 1 over mu raised to power y squared by 2 minus x squared by 2. Actually, most of the information is in the exponent, so it's easier to work with the exponents. So we take log base 1 over mu of these densities, and we call them log densities. So if I want to draw the upper bound for log densities, this figure shows log densities in terms of distance from the query. Now let's analyze the evolution of query's bucket overall this process. First, assume that the query always lies on the sphere. Remember that in the procedure, we will finding and removing dense clusters from spheres, so the sphere will look pseudo-random after the first round, meaning that most of the points are orthogonal to the query on this sphere. So they are at distance root 2 times r from the query. Now let's check an example and see how this spherical hashing ground is going to affect log densities. Suppose that first we start with a data set that has the following log densities. By the point that I just mentioned, this data set should lie on a sphere of radius r1, so that most of the points are at distance root 2 r1 from the query. Now we do a round of spherical elicitation removing dense clusters. We end up with a query bucket that has the following log densities. As you may have noticed, the maximum has moved to the left on the red figure. Now we should lie on a sphere that has radius root 2 times radius r2, so that the distance to this maximum is root 2 times r2. We do the same thing on this sphere, and we end up on a new sphere, and so on and so on. The main challenge is finding the worst trajectory over all these spheres and tracking the density evolution over the worst trajectory. We took several technical steps to prove our result. The first step that we took is that we proved that the worst case is when the query is on the sphere. The second step that we took is to show that the worst case is actually when the sequence of radii is decreasing. Then using these two steps, we were able to reduce the query time analysis into solving a linear programming that we solved numerically. So in summary, for the Gaussian kernel, our data structure has a space order 1 over mu, and its query time is 1 over mu raised to power 0.173. The approach and the ideas in the analysis can be applied on a broad class of kernels, but not all of them. There are a bunch of open questions in this area. One main question is that how can we simplify the data-dependent analysis? This actually raises the question of, can we simplify the LSH functions used in data-dependent LSH for approximate near-neighbor search problem? We actually made some progress in this work, in this area. We were able to simplify the algorithm and their analysis a little bit, but I think that there are so many things to be done there. The second question is that what is the optimal solution and optimal exponents for this problem? And finally, it would be nice to have a practical version of this algorithm. Thank you for your time. If you have any questions, you can send me an email, or we can talk over the Q&A session in this conference. Thank you.